As I said in an earlier lecture, the two important things that you study when you study an abstract mathematical structure is 1. You study substructures, and 2. You study special maps between the structures. The substructures, of course, means subgroups, something which we have already studied in some detail in an earlier video. We are now going to study maps between groups. We are not really interested in any map between two groups. We are interested in maps which preserve the basic mathematical structure that we are studying. And in this case, we are interested in the group properties. So what we want to study are maps which, in a sense, preserve group structure. Now, exactly what does that mean? Well, that is what we are going to discuss now. Now, given two groups, G1, star 1 and G2, star 2, let me point out that at this point, I am being very precise about stating the group as an ordered pair of the underlying set and the product operation. Whenever the underlying set or the product operation is sort of obvious from the context, we will stop labeling them as G1, star 1 and so on. We are going to stop being so detailed. But for the time being, because we are introducing the concept of maps between two groups, we have two groups. We want to be precise here. We have two groups, G1, star 1, that is, the underlying set is G1 and the composition rule between elements is star 1, and G2, star 2. Maybe a different underlying set, maybe a different composition rule. A map F from G1 to G2 is called a homomorphism if it is onto and it obeys this particular relation. For all small g and small g prime in G1, the domain of the map, if acting on G star 1 g prime, that is, g and g prime have been composed according to the multiplication rule in the group G1, and then you have applied F to it, this has to be the same as f of g composed with f of g prime, where the composition rule that you use now is the rule for the second group, star 2. Now, at this point, let me also emphasize that the restriction that a homomorphism has to be onto is not a universal one. Not all authors impose this particular restriction. However, we are going to insist on a homomorphism being onto simply because it makes it easier to state a lot of theorems that we will have occasion to state later. So, if you have a structure preserving map, that is f of g prime is f of g prime, which is not onto, then what you can always do is you can show that the image of G1 under the map is a subgroup of G2, and then you can also talk about our kind of homomorphism, that is an onto kind of homomorphism between G1 and that particular subgroup of G2. But usually we should not have to worry about these things because most of the maps that we will deal with will be onto automatically. As you can see, the map F has this nice structure preserving property. Note that the only structure that you have in groups is the product, and here what F is doing is that if you do the product first in the first group and then apply F, the result that you get is the same as the one you would have obtained by applying F on the individual pieces and then applying the product in the second group. In this sense, the groups G1 and G2 have similar structure. Why am I saying similar but not the same? The reason will be clear from the examples that you will see soon. In this context, we have this definition. The two groups are going to be called homomorphic if there is a homomorphism between them. And the notation that you use here is G1 tilde G2 or G1 sim G2 is written if G1 and G2 are homomorphic. Before we go any further, let us discuss a few examples of homomorphisms between two groups. For our first example, we will take the case where G1, the first group, is a set of all integers under addition, and G2, the second group, is Z3. Z3 is a set of integers 0, 1 and 2, and the operation here is addition modulo 3. A bit of thought will convince you that this is essentially the only group that you have of order 3. Or rather, as we have seen before, there is up to relabelings, there's only one group of order 3, and Z3 is an example of such a group. Now, we are claiming that these two groups are homomorphic. So how does it work? For this to work out, you need to show that there is a homomorphism between them. That is, you have to show a map between G1 and G2 which preserves the structure. In this case, the multiplication structure in the two groups, which in this particular case happens to be addition for the first group and addition modulo 3 for the second one. So let us consider this simple map phi, which maps Z to Z3, and where it takes an integer n, a member of the group Z, to the value n mod 3, which is just simply the remainder which you get when you divide n by 3. Of course, this result is actually any one of 0, 1 or 2, and it is very, very elementary number theory to show that if you add two integers and then map it using this map phi by taking its remainder after division by 3, the result is the same as the one you would get by taking the remainders first and then adding them modulo 3. So this is an exercise which you should be able to do very easily. Prove that this particular map preserves the group structure and allows you to map one group into another homomorphically. So this was our first example of a homomorphism. It should be pretty clear from this particular example why I say that two groups which are homomorphic does not necessarily have to be like each other. In this particular example, G1 happens to be an infinite group, whereas G2 is a nice finite group with only 3 elements. So they are not really very similar, but somehow they share something about their structure which the homomorphism is bringing out. In fact, at least in this case, the two groups are abelian. Even that will not be respected by our next example. The next example of homomorphism that we are going to talk about involves that between a non-abelian infinite group and an abelian infinite group. So here the first group G1 is GLNR, the set of all n by n invertible real valued matrices, and the second group is that of all non-zero real numbers under multiplication. And the claim is that there is a homomorphism between these two groups. And the homomorphism is actually a pretty familiar one. Let us consider the map which I am calling det, and it's a map between GLNR to this set of all non-zero real numbers. And what that map does is that it maps a matrix M, a member of GLNR, to its determinant. Remember, all matrices in GLNR are invertible matrices, so the only possible values for the determinant of M are non-zero real values. But all possible non-zero real values are actually allowed. So this is an onto map, and the fact that it actually preserves group property, that is, in this case the property of matrix multiplication, is a familiar result that all of you know. All this is saying is, if you take two matrices M1 and M2 and you multiply them using the standard rule of matrix multiplication, which is the product in the set GLNR, then determinant of M1, M2 is simply det M1 times det M2, where the times in the second case is simply the actual multiplication of real numbers which you use in the second group. So this is an onto map which preserves group structures. In this case, the two group structures are rather different. A non-abelian group for GLNR and an entirely abelian ordinary multiplication for the group G2. But yet, we see that there is a homomorphism between these two groups, and the groups hence are homomorphic. The two examples we have seen so far involved two rather dissimilar groups. Apart from the fact that the homomorphism preserved the structure of the group composition rule, there were very little similarity between the two groups involved in both the cases. We are going to look at a different kind of example next. The two groups that we will talk about now look very different at first sight, but that is a case of appearances being deceptive. The group G1 here is the set of all real numbers under addition, and the group G2 is the set of all positive real numbers under multiplication. Our first claim is that they are homomorphic to each other, that is, there is a homomorphism between R plus and R plus times. So what is this homomorphism? In fact, this is a homomorphism which is very familiar to all of you from elementary mathematics. The map that connects the two, which essentially changes the addition into a multiplication, is a map which we know as the exponential function. So if you take any element from the set of real numbers, apply the exponential to it, of course you get a positive number, and in fact you get every positive number as a result of this. On the other hand, is elementary mathematics which tells us that if you exponentiate x1 plus x2, you are going to get e to the power x1 plus x2, which is e to the power x1 times e to the power x2. That's really the product of x1 and x2, which means that in the second group, the multiplication rule, which here is the ordinary multiplication of numbers, can be applied after you map the elements, or you could apply the map after applying the multiplication rule in the first group, which is plus simple addition. So this is of course an example of a homomorphism. Actually, it's more than that. Again, something that you all know is that this map has an inverse. The inverse is a well-known function, logarithm, which takes any positive real number to the real number. And that also preserves the group structure in this case. So what happens is that in this case, the homomorphism actually works both ways. And that's because the map exp is 1 to 1. And not only that, its inverse is also a homomorphism. So such maps are called isomorphisms, and we are going to spend quite a lot of time talking about them. In fact, we have already alluded to isomorphisms several times before, wherever we have said that there is only one group with 2 elements, or only one group with 5 elements, or these two groups are the same group, essentially. What we have really meant is that there is an isomorphism between the two groups. Before we start discussing isomorphisms in earnest, let me just quickly recount a couple of very important properties which all homomorphisms have. So, let us consider F, which is a homomorphism between two groups G1 and G2. Of course, F is just a map between the underlying sets, and as usual, we are confusing deliberately the distinction between a group and its underlying set. And when I say F is a homomorphism from G1 to G2. Well, if such is the case, then one very important property immediately follows, which is if you apply F, the map, on E1, which is the identity in the group G1, the result is the identity in the group G2. That sort of sounds obvious, but the formal proof of this goes this way. For all small g which belongs to capital G1, let us try to form f of g times f of E1. Now, notice that I have sort of moved away from the very precise and specific way of writing things that I used a while ago. The star here, the star between f of g and f of E1, is of course star 2, the product in the group G2. But according to the fact that this is a homomorphism, this has to be equal to f of g star E1, and this star of course is star 1, the star in the group G1. From now on, I'm actually not going to specify which star I mean, simply because it should be obvious from the context. In fact, a while later, we are just going to drop the star altogether and just use AB when we mean A star B. But in each case, the particular product that we have in mind has to be decided from the context. In this case, f of g star E1, of course, is f of g because E1 is the identity in the group G1. But then what we have is f of g star 2, f of E1 is f of g. And by using the simple cancellation property in a group, and G2 is a group, we end up with f of E1 equals E2, the identity in the second group. Now, another very important and useful property follows almost immediately, which is for every element small g of G1, f of g inverse is actually the inverse of f of g. Note that once again the two inverses actually refer to the two different operations involved here. G inverse is being carried out according to the product rule in the group G1, whereas f of g's inverse is according to the product rule in group G2. And how do you prove this? Well, it's pretty simple. All you do is check what f of g inverse times f of g is, and here note that I've just dropped even writing the star. This of course has a star in between f of g inverse and f of g, and that star is star 2. But as I said, it's sort of obvious from the context. So f of g inverse f of g is, according to the standard property of homomorphisms, the same as f of g inverse g, and g inverse g, here of course the star between g inverse and g is star 1, and g inverse g is of course E1. So this is f of E1, which we have already seen is E2. So f of g inverse star 2 f of g is E2, and that simply tells you that f of g inverse is the inverse of f of g. Let us now turn to this very important concept of isomorphism. Now, as I have said, an isomorphism is actually a homomorphism which is invertible. In other words, a homomorphism which is a bijection is called an isomorphism. Now, let me point out that we did not really explicitly demand that the inverse map is also a homomorphism. The reason why we did not do that is that it is rather easy to prove that at least for homomorphism between groups, the inverse map of a homomorphism, if it exists, is also a homomorphism. It's a rather simple exercise, but not completely a trivial one. So you should try your hand at it. So that is why we are not demanding that the inverse map is also a homomorphism, because that automatically follows from the basic definitions. So all we have to demand is a homomorphism be a bijection. Of course, in our definition of a homomorphism, I've already assumed that it's an onto map. Therefore, all we really have to prove is that a homomorphism has to be a one-to-one in order to be an isomorphism. As I have been saying, isomorphic groups which have isomorphism between them, they're identical as far as the group structure is concerned. The elements involved may be very different, the product rule may be different, but as far as the group structure is concerned, apart from relabeling, they are exactly the same. You write this isomorphism between two groups using this sym-equal sign, that is, it's sort of like the homomorphism sign but with an additional equal to added to it. Just to emphasize that if two groups are isomorphic, then they are almost, well, as far as group structure is concerned, they are identical. In addition to this, we can say something rather trivial, which essentially follows from what I just said. Two groups are isomorphic if and only if they have identical multiplication tables. Of course, the multiplication table may look rather different if you have labeled the elements differently, but you can always relabel elements in such a way that the multiplication table end up looking identical. In fact, this relabeling of elements is exactly what the isomorphism does. Now for some examples of isomorphisms. The first example of isomorphism is one that we have been using from the very first lecture. In the very first lecture, we looked at our first example of a group, which was a set of all symmetries of an equilateral triangle. And we also pointed out that in one-to-one correspondence to every one of those symmetry operations was a permutation which permutes the three vertices of the equilateral triangle. And these two sets and the underlying multiplication structure were so close to each other that so far we have actually said that the set of symmetries of an equilateral triangle is S3, where S3 is actually the set of permutation of three objects. So I will not try to prove to you that this is an isomorphism. If you take a look back at the first video, you will find the fact that this is an isomorphism sort of laid out there without just using those words. But the next example that we are going to look at is slightly less trivial, which is this one. In fact, we have already said this before. While we were describing the quotient group, we have said GLNR quotiented by SLNR, this particular quotient group, is in essence the same as the set of all non-zero real numbers under multiplication. I want to formalize this by showing that there is an isomorphism between these two groups, the quotient group on the one hand and the set of all non-zero real numbers under multiplication on the other. Now, to show that, what we need is an isomorphism, an invertible homomorphism between the two groups. So what we really need is, we need to show that there is a homomorphism and that this homomorphism is one-to-one. Now, the homomorphism is one which we have actually already talked about in the last lecture. The map phi, which maps a coset, which of course is what an element of GLNR by SLNR is, it maps a coset labeled by the matrix M, the coset M SLNR, which of course is a set of all matrices that you can obtain by multiplying M by elements in SLNR. The map phi maps the coset into determinant of M. Just to point out again, I've already done that in the last lecture, but still let me remind you that this is a well-defined map, because no matter which matrix you choose from this coset to label it, they all have the same determinant. So the number that you get as a result of applying phi to M SLNR is unambiguous. You get the same no matter which representative you choose. The claim is this is a homomorphism. For that, what we need to show is that this preserves the multiplication structure. Well, when you multiply two cosets M1 SLNR and M2 SLNR and then apply phi on it, well, we can always multiply first. We know the way in which multiplication works here. The multiplication for cosets or with respect to a normal subgroup is simply M1 M2 SLNR. There's a standard rule. That means this coset is labeled by the matrix M1 M2. So according to our rule, phi maps this onto the determinant of M1 M2. And now elementary matrix algebra takes over. Det M1 M2 is nothing but det M1 times det M2. And det M1 is phi of M1 SLNR. And det M2 is phi of M2 SLNR. So what we have shown is that this map preserves the group structure. You can multiply the cosets first and then apply phi, or you can apply phi first and then multiply the numbers, and you get the same result. Now, what I want to emphasize at this stage is that there is one more thing you need to prove before we accept this as a homomorphism, which is that this is a onto map. All you need to show for that is that no matter what non-zero real number you give me, I can always give you a coset M SLNR which gets mapped to that. In other words, all you have to do is give me a matrix with any arbitrary number as determinant. That can be done is very, very easy to figure out. So our map phi is a homomorphism. It preserves group structure. It's also onto. Is it one-to-one? Well, let's check. I'm claiming it is also one-to-one. But to check that, we need to show that whenever two cosets map onto the same result, they must be the same coset. And how do you show that? Well, you start by assuming M1 SLNR and M2 SLNR give you the same result when you map them using phi, which of course means the determinant of M1 is the same as determinant of M2, and that immediately tells you that M1 M2 inverse has a determinant of 1, so it belongs to SLNR, or in other words, M1 belongs to the coset M2 SLNR. So the coset M2 SLNR can be labeled, as we have been saying, by any one of its elements, so it can also be labeled by M1, and hence M2 SLNR and M1 SLNR must be the same coset. This establishes the fact that this map phi is 1 to 1, and so what you end up with is we now have a homomorphism between the quotient group GLNR by SLNR and the set of non-zero real numbers under multiplication, which is not just a homomorphism, it's also a bijection. So this is an example of an isomorphism between two rather dissimilar looking groups, but this also tells us what we have been saying from the last lecture onwards, that this quotient group is actually the same as the set of non-zero real numbers under multiplication. When I say actually the same, I of course don't mean the elements are the same or the multiplication rule is the same, but the structure that you get under multiplication is exactly the same. So as far as groups are concerned, they are the same group. For our next example, we will consider a case where both the groups G1 and G2 are the same group. In fact, they are both the same as GLNR, a group which we have used in several of our examples, in fact even the last example. Now, what we are going to do is we are going to first write down a map from G1 to G2, in this case of course from GLNR to GLNR, and then we are going to show that this map is an isomorphism. The map we have in mind involves choosing a particular fixed matrix M in GLNR and then defining the map phi M in this fashion. Any matrix P in G or G1 or G2, whichever one you want to call it, is mapped under this phi M to MP M inverse. Of course, this is a very familiar map to all of you. This is nothing but doing a similarity transformation on the matrix P induced by the matrix M. Now, it's very easy to see that this is a homomorphism. In fact, the proof that this is a homomorphism is one which is very familiar to all of you, although you have seen it perhaps not in this language, but you have definitely seen this in linear algebra. So what does phi M do to P1, P2? It of course multiplies P1, P2 by M on the left and M inverse on the right. And the next step that I am going to carry out should be obvious to all of you, at least all of you who have seen this in linear algebra before. You just put in a M inverse M, that is the identity, between the P1 and the P2. So you end up with MP1 M inverse, MP2 M inverse. And MP1 M inverse is obviously phi MP1 and MP2 M inverse is phi MP2. So this proves that this map phi M preserves the group structure in GLNR. When you map P1, P2, what you end up with is what you get when you map P1 and P2 separately and then multiply them. Now it is obviously 1 to 1 for the simple reason that if MP1 M inverse is equal to MP2 M inverse, that is phi MP1 is the same as phi MP2, then by the cancellation law for groups, or simply from the fact that matrix multiplication allows you to cancel with invertible matrices, you end up with P1 equals P2. So this is a map which maps GLNR into itself, and at the same time it's a homomorphism, is also obviously 1 to 1. This last example was of a special kind of isomorphism, an isomorphism of a group into itself. Such isomorphisms form a class of their own, and they are called, rather obviously, automorphisms. An automorphism on a group G is an isomorphism from G to G. The set of all isomorphisms on a group G form a group and this is called AUT-G. AUT, of course, is short for automorphisms. But why are we so sure that this is a group? Let's check whether the set of all automorphisms on a group G actually form a group. For that, we need to check all the group properties. So let us take any two maps from AUT-G, and they are both isomorphisms, of course, curly G1 and curly G2. Then the map curly G1, curly G2, one operation after another, is obviously a map from G to G. And since G1 and G2 are both automorphisms, they are both onto maps, they are both invertible. So G1, G2 is of course also invertible. But the question is, does G1, G2 preserve group structure? Acting on a product GG prime, what does it do? Well, for all small g and small g prime, capital G, curly G1, curly G2 acting on GG prime is really curly G2 acting first and then curly G1 acting on the result. Now curly G2 being an automorphism, hence being structure preserving, produces curly G2G, curly G2G prime, and then curly G1 goes and acts on that. And curly G1 is now acting on the product of curly G2G and curly G2G prime, so it produces curly G1 G2 G times curly G1 G2 G prime. So curly G1 G2, as we have been claiming, does preserve group structure, and being a composition of two bijections is obviously a bijection. So curly G1 G2 is also an automorphism. So at least the set AUT-G is closed under composition. So it passes the first of our tests for being a group. Now, group multiplication must be associative, but in this case, because we have defined multiplication via composition, that is, you do one operation after another, associativity is sort of trivial. So we don't need to really check it. What about the identity? The identity map from G to G, which maps every small g to the same element, is obviously an isomorphism, so it is in AUT-G. And the inverse of every automorphism exists, and this is a trivial statement because an automorphism by default is a bijection. So it has to be invertible, and its inverse exists. And as I have said before, at least for group isomorphisms, you don't really have to check whether the inverse is also an homomorphism, because that follows trivially from the basic properties of the group. Let us now turn to an example of AUT-G for a particular group G. The group G that we have in mind is a group that we had met before. This is a Federer group V4, or the Klein-4 group, which, let me remind you, is generated by two generators A and B, which obey this relation A square and B square equals the identity, and AB commutes so that AB equals BA. We had studied this group in some detail in a previous lecture. We had formed its full multiplication table, and it's called the 4 group simply because it's made out of 4 elements. AB, apart from A, B and E, is the 4th, and AB also turns out to obey AB whole square is identity. A physical realization of this is simply the set of all symmetries of a rectangle, a non-square rectangle. Now, let us consider all automorphisms possible on V4. Now, automorphisms being bijections must obviously be permutations of these 4 objects, E, A, B and AB. Let's call that C. E, A, B and C. So if curly G is a member of the automorphism group of V4, then curly G must be one of the permutations of these 4 objects. So it must be an element of S4. However, not all elements of S4 are in AUT V4 because all of them are not automorphisms. Why not? Well, it's very easy to see that an automorphism must map the identity to the identity. So All permutations, of course, don't do that. So all permutations of 4 objects obviously are not automorphisms. Given the fact that we have to keep E fixed, we have still 3 more elements A, B and C to play with. And it turns out that all permutations that fix E are indeed automorphisms of the group V4. Now that's really not a trivial thing to say, so let us take some time to think about why it should be the case. Note that what we are demanding is that whatever curly G is, when curly G acts on A, it must produce something which squares to the identity, simply because A square also squares to the identity, and that is what a homomorphism will demand. But that in itself is not a huge restriction, because all the 3 elements of the group, other than the identity, all of them are non-identity elements, of course, but they all square to the identity. So curly G of A could be any one of A, B and C, and that would not violate the demand that whatever it maps onto has to square to the identity. Okay. So A can be either A, B or C. Of course, B can now be any one of the other elements available. Identity, of course, is already taken as the image of E. And remember, these are bijections, so you can't have repeats. They are 1 to 1, of course. And so whatever element among A, B and C that A goes to, B has to go to another element. Once again, B square being the identity means curly G B square has to be curly G acting on E has to be the identity, which translates to curly G B times curly G B is the identity. But that's not an extra restriction, simply because curly G B could be any one of A, B and C, and all of them square to the identity. Anyway, however, once you have fixed curly G A and curly G B, you have no choice about curly G C, because curly G C must be the product of these 2. However, a moment's thought will tell you that in the case of the Fourier group A, this restriction that curly G C has to be curly G A into curly G B does not really impose any further restriction other than the demand that whatever A and B map to, C must map to another element. And that means there's only one choice left, because E is anyway out. So it's rather easy to see that the only restriction that you have on the automorphisms of V4 is that the identity has to be the identity. Other than that, all permutations of the 3 objects A, B and C do qualify as automorphisms of V4. I would urge you to take pen and paper and try to construct these automorphisms. Just ask yourselves, what are the possibilities of E, A, B and C mapping to, and try to figure out that they do obey the homomorphism demand which an automorphism must satisfy. And when you compose 2 automorphisms, of course, it's rather easy to see that the corresponding permutations of A, B, C will get composed. So it so turns out that automorphism group of V4 happens to be essentially the same as the group of permutations of 3 objects. Just to repeat, why 3? Because out of the 4, identity cannot move from being the identity, because all automorphisms, indeed all homomorphisms, map the identity to the identity. So leave that aside, the other 3 objects can permute themselves in whichever way, and all of these permutations are consistent automorphisms. Let me point out one thing, the fact that all permutations of the objects other than the identity happen to be valid automorphisms work for this particular group. It does not work for all groups. Just as an exercise, why don't you try to figure out the automorphism group for the other group with 4 elements, namely C4. That should really convince you that the thing is a bit more non-trivial than that. Now the other example of automorphisms that we have seen was that on GLNR, where we carried out the automorphism by doing a similarity transformation on matrices. This, of course, is nothing but a special case of the conjugacy operation on a group. And in fact, it so turns out that there is a whole special class of inner automorphisms. So these are called inner automorphisms. They arise from conjugacy. For all small g in capital G, we can define a map I small g, which maps capital G to capital G by this rule. I small g acting on G prime will be G, G prime, G inverse. We had actually met the map I small g in a previous lecture when we were talking of conjugacy classes, but there we did not really formally name this. Right now, let us name this formally. This is the inner automorphism induced by the element small g. Now, the name really is justified, but to see this, we have to check that I small g is actually an automorphism. Well, to check whether it is group structure preserving, all you have to do is apply I small g onto the product of two elements G prime, G double prime, where G prime and G double prime are any two elements from our group capital G. So by definition, what I small g does to this is that it pre-multiplies or multiplies on the left G prime, G double prime by G, and on the right it multiplies by G inverse. And by now it should be obvious to you what we should do. We play exactly the same trick that we did in the case of matrix similarity transformations. We just put a G inverse G equals identity in between G prime and G double prime. So this becomes G, G prime, G inverse, G, G double prime, G inverse. And that of course is IG, G prime times IG, G double prime, which is exactly what you need for IG to be a homomorphism. That IG is a bijection is actually again a trivial result from group theory. And I urge you to check for yourself whether you can prove this. So IG is an automorphism. Now the collection of all the possible inner automorphisms on a group capital G is obviously a subset of odd G. It's actually pretty easy to show that this set or collection curly I of G of all inner automorphisms on G happens to be a subgroup. In fact, it's pretty trivial to show that IG1, IG2, two inner automorphisms, when multiplied, in this case, of course, multiplication means composition, gives rise to IG1G2. And the fact that this obeys all other group properties apart from closure, which we have just stated, is rather easy to show. So curly IG is a subgroup of odd G. What we are claiming here is that not only is it a subgroup, it is a normal subgroup of odd G. To see this, let us do the following. We will start with any arbitrary element curly G from odd G and pick any I small g, any inner automorphism which is in curly I of G. And let's try to see whether curly G, I small g, curly G inverse is actually an inner automorphism. Now, if this claim that I have made right now is true, then this automatically shows that curly I of G, the set of all inner automorphisms on G, is invariant under the action of curly G, or invariant under conjugation by curly G. And because this curly G is completely arbitrary, this just goes to show that curly I of G is a normal subgroup or an invariant subgroup of the group odd G. So let us verify this particular claim. To see what curly G IG, curly G inverse really is, what we need to do is see what it does to any arbitrary element of the group. So let's try to pick any arbitrary element of the group. We have denoted it by G bar. The bar simply serves to distinguish it from the G index on the particular inner automorphism we are talking about. So I could have called it any other letter. This G bar seemed to be a right thing to use. So what does this curly G, I small g, curly G inverse mean? Here, of course, each one of these are maps, and so the product of these maps is basically composition. So it's really curly G acting last on I small g acting on curly G inverse G bar. That's all there is. Now, I small g acting on curly G inverse G bar is really small g curly G inverse G bar times small g inverse. Now, curly G gets to act on this whole thing. This, remember, is a product of three terms: small g, curly G inverse G bar, and G inverse. Curly G, being an automorphism, is obviously a homomorphism, and because it's a homomorphism, curly G can act on each one of these things separately. So you get curly G of G, then you get curly G inverse of G bar, which is just G bar, then curly G of G inverse. So this is what you end up with. And we then use another property which all homomorphisms have, and we have already established near the beginning of this lecture. Curly G acting on G inverse is curly G whole inverse. So let's just use that. And this shows me that curly G inverse is actually the inner automorphism generated by curly G. So this is what curly G inverse is. I curly G of G, which of course is a member of the set of all inner automorphisms. And this works for all I small g. That is, if you do curly G I small g curly G inverse for all possible I small g, then the result is always in curly I of G, and hence, as I've said, curly I of G is actually invariant under the conjugacy by any element curly G of odd G. This is exactly what we mean when we say curly I of G is a normal subgroup. Now, of course, if you have normal subgroups, then you can also produce a quotient group or a factor group using this. Remember, in a factor group, cosets of the normal subgroup are really the elements. And when you say cosets of the elements, what you are really doing is that if two elements are congruent modulo the normal subgroup, you lump them together in one single conjugacy class. In a sense, automorphisms which differ only by an inner automorphism are sort of identical. The cosets that we are talking about here basically lump all the automorphisms which differ only by an inner automorphism together into a single element. So what we are really looking at are essentially different automorphisms when we consider this group called the group of outer automorphisms. I hope this will be clearer later when we see more of this in action. In this lecture, we met several maps or several kinds of maps from one group to another, and we were of course interested only on those special kinds of maps which preserve structure, that is homomorphisms. We also saw that homomorphisms of a special kind are very, very important. They are homomorphisms which are bijections. They essentially tell you that two groups are really identical. And among isomorphisms, you have a special class of isomorphisms which map a group G into itself. And we studied all of that and studied a few examples in this lecture. But one question might very well have bothered you by now. Every isomorphism, after all, is a homomorphism. So is there a way which allows us to tell, given a homomorphism, is this really an isomorphism? Or, if you just have a homomorphism which is not an isomorphism, can you somehow manipulate that into giving you an isomorphism? The answer to both these questions lie in very important results in abstract group theory called the isomorphism theorems. These theorems are going to be our topic in the next lecture.